Welcome back. The objectives of this video are to introduce summation notation. We'll take a look at properties of sums, we'll introduce series, and we'll find the sum of a series. So let's take a look at summation notation, something that you'll see quite often in calculus. There's a convenient notation for some of the terms of a finite sequence. It's called summation notation or sigma notation because it involves the use of the uppercase Greek letter sigma. So given our summation or our sigma here, we can represent the first n terms of a sequence by saying the sum of I to n of a sub I equals a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, etc. Where I is the index, n is the upper limit because it's on top, or it's on top because it's the upper limit, and 1 is the lower limit, and it's below of our summation. So we'll evaluate from 1 to n, from our low to our high. So let's look at a couple of samples here. In sample A, let's look at the sum of all values beginning at I equals 1 all the way to 5 of 3i. So they're telling us we want to substitute 1 into 3 times I, and then 2, and then 3, and then 4, all the way until we get to 5, and then add those together. So 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. Or you could also do this as 3 times 1 plus 2 plus 3 plus 4 plus 5. So we're substituting 1 through 5 into the expression and then adding each interval. So 3 times 15 is 45. In sample B, we're looking at the sum of 1 plus k squared from 3 to 6. So we're going to substitute 3 and then 4 and then 5 and then 6 into our expression and then add each value. So we'll start with 1 plus 3 squared, which is 9 plus 1 is 10. We'll add it to 1 plus 4 squared, which is 17. We'll add that to 1 plus 5 squared, which is 26, and we'll add that to 1 plus 6 squared, which is 37. We add those values, 10 plus 17 plus 26 plus 37 equals 90. In our third sample here, we're going to evaluate 1 over n factorial from n equals 0 to 8. Individually, we're going to substitute 0 through 8 into the expression and add the results. 1 over 0 factorial, 1 over 1 factorial, all the way to 1 over 8 factorial, and add each of those individual values. 0 factorial is 1, 1 factorial is 1, and then 1 over 2, 1 over 6, 1 over 24, and so forth. When we add those all together, if we added them all the way to infinity, we would get a number that looked like about 2.71828. You might recognize that result as our value of e. So the value of e is the same as 1 over n factorial if we go from 0 and all the way to infinity. Welcome to calculus, gentlemen. Our sample 4, find the sum of 4i plus 1 from I equals 1 to 4. So we would complete that problem. We're going to substitute 1 in for I, multiply it by 4 and add 1. So 4 times 1 plus 1 is 5. And then we put 2 in. So 4 times 2 plus 1 is 9. Put 3 in. 4 times 3 plus 1 is 13. 4 times 4 plus 1 is 17. Add 5, 9, 13, and 17, and we get a value of 44. So the sum of 4i plus 1 from 1 to 4 is 44. Summation notation, you can read this remark here, but essentially summation notation helps you generate the appropriate terms of the sequence prior to finding the actual sum. And then we've got some properties of sums here. The sum of c from I to n is essentially equal to c times n, where c is a constant. It'll always be the same. In example 2, c is kind of a scalar here. C times a sub I to n is the same as c times the sum of a sub I. And then we have the sum of a sub I plus b sub I from 1 to n is the same as the sum of a sub I plus the sum of b sub I. So the sum of the quantity a plus b is equal to the sum of a plus the sum of b. Same for subtraction. The sum of the quantity of a minus b is the same as the sum of a minus the sum of b. Our next objective is to take a look at series. There are many applications that involve the sum of terms, both finite or infinite sequence, or an infinite sequence, and these are called series. The sum of the first n terms of a sequence is called a finite series, or the nth partial sum of the sequence. And it's denoted by a sub 0 plus a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n from 1 to n. So for a fixed number of terms that we're evaluating, that would be a finite series or a partial sum. So if we have a fixed number of terms we're looking at, we have a finite series or a partial sum. If we're looking to find the sum of all the terms of an infinite series or an infinite sequence, it's called an infinite series. In those, we're going from 1 all the way to infinity. We have to include everything. Our objective 4 here, to find the sum of a series. So we're given this series, 3 over 10 raised to the I, and we want to look at I from 1 to infinity. Well, they're asking us to find here just the third partial sum. So we don't have to find all of them. We'll just look for the first 3. So we'll evaluate our series for I equals 1, I equals 2, and I equals 3. And we'll add each of those together. So let's see what that looks like. I equals 1, the sum of I equals 1 to 3 of 3 over 10 raised to the I. We have 3 over 10 to the first, plus 3 over 10 to the second, plus 3 over 10 to the third. We get 3/10. Might be easier to see it this way. 3/10 plus 3 100ths plus 3 1,000ths. Adding all those together, we get 0.333. This is just our tenths place, isn't it? And our hundredths place and our thousandths place. And in the next sample, we're given the same series. We've already found the third partial sum of this, but now they're asking us to find the sum of this series. That we're going to evaluate from 1 to infinity. I'm not going to ask you to do this by hand. It would take a while, but once you figure out the pattern, you'll see here that each one of these is our tenths place and our hundredths place, as I mentioned before. So we evaluate that, we continue that on. This is going to become 3 or 0.33 repeating, or as we know it, 1/3. So that concludes our introduction to summation notation and finite and infinite series, and we'll get some more practice with this when I see you in class.